Okay, so we're going to talk today about very important compounds, transition metal olefin complexes, alkyl complexes, and their decomposition. Now, we encountered some of this in the 2000 course, right, when we had the introduction to organometallic chemistry. And again, there's different ways of classifying ligands in organometallic chemistry. Different people do it in different ways. In Olschenbuch, the Bible, they do it in terms of sigma and pi capacities of the ligands. A similar way of doing it is simply in terms of hapticity. In other words, how many contiguous carbons in a ligand are actually bound, carbon-containing ligands are bound to the metal centers. So remember, in organometallic chemistry, we're thinking about metal-carbon bonds. Now, here's some examples. We have alkyl complexes, E1. Also, aryl compounds fit in there, sigma-bonded aryl. We have carbenes, or we could carbides. These are also E1. We're going to be discussing that today. Olefin complexes, which are hapto-2 coordinated, which we're also going to look at today. Incidentally, you also have, as we saw in the tutorial, the possibility of a hapto-2 coordinated alkyne. So that's also a possibility. Here we have an interesting allyl ligand, here shown in its hapto-3 coordination mode. Remember, we discussed this last semester. This thing can undergo a hapto-1, hapto-3, so-called haptotropic shift, and then it goes from the hapto-3 to the hapto-1 mode, and so on. There's a butadiene, that's hapto-4, cyclobutadiene, hapto-4, hapto-5, this classic ligand CP we're going to be discussing next week in detail, and arenes, which you're working with in your practical. So I would say that the best way to sort of organize ligands is by looking at their hapticity. Now today we're going to look at alkyl ligands, which are a very important class of compounds in organometallic chemistry, particularly because they're vital in many catalytic processes. Here I give one example, olefin polymerization, but there's also other catalytic processes where they're very important. For example, coupling reactions. Maybe you've heard a bit about that in organic chemistry. CC coupling reactions, head couplings, Stiller coupling, and so on, all involve alkyl or sigma-bonded aryl complexes. The problem is they're kinetically unstable, so it's a challenge to isolate them because they tend to be susceptible to decomposition reactions. And that's what we're going to be looking at today, is their reactivity and their decomposition, and why that's important. Now, you can think of the bonding interaction between this sp3 hybridized carbon here, so this is a generic alkyl in a metal, as essentially a sigma donation of this sp3 hybridized orbital bearing a lone pair of electrons into an appropriate d-metal orbital. Another way of looking at it, that's if you go with the ionic counting methodology, if you treat it as a -1 donor. Another way is to think of that you have one electron in this orbital, one electron in the metal orbital, and they form a covalent bond. Remember, it depends on how you do the counting, whether you do ionic or covalent. So, what I want us to do now is build up a toolbox of reactions that we can employ to make these things. Now, we looked at some of this already last semester, remember? So this is like, some of this is revision. And the most commonly used way of installing an alkyl chain or an alkyl group on a transition metal, also a sigma-bonded aryl, pretty much works in the same way, is by doing metathetical exchange. In other words, you start with a transition metal complex that has halides attached to it, and you react it with some reagent that bears a nucleophilic carbon. And the way that you do that, here R represents alkyl or aryl, is by basically using lithium reagents. You can use Grignard reagents, a whole array of these. If you look at the polarity, because the metal is electropositive, it results in a nucleophile residing on the carbon atom attached to these metals, and they become hot nucleophiles which can then attack the metal. You get metathetical exchange, as we can see here, and you install the alkyl group R on the metal. So this is very similar to what we have in organic chemistry, right? What do we have in organic chemistry? I mean, mechanistically it's different, but in principle it's the same. If you take this molecule here, what happens? Substitution, right? Nucleophilic attack, that's the leading group, and you get a so-called Walden inversion, remember? And you get the product. Now, that's basically what's going on here. It's a nucleophilic, you can think of it as a nucleophilic substitution. You generate a nucleophile on the alkyl chain because of its attachment to an electropositive metal, right? So, let's take, for example, lithium CH2R. This is delta plus, this is delta minus. So the attachment to, for example, lithium makes this into a nucleophilic center, which can then attack an electrophilic metal, and you use the chloride is a leaving group. Now that's not strictly speaking correct, the mechanism is a little bit different, but there is sort of the way to remember it is to think about organic chemistry, right? Nucleophile attacking an electrophile. Now, I want to make another point at this stage. Every chemist in the world has gone through the same process, and that is a process you have to learn certain reactions. You can't get around that. It's like being a carpenter and building a table. If you don't know what tools you have available, you're not going to be able to build a table. And before you can apply the principles of organometallic chemistry to problems, you have to build up the tools. That unfortunately involves quite a bit of learning, much the same way as in organic chemistry. But what I'm going to try and do is to teach you these reactions in a way that you can sort of understand them. Not that you learn, I don't want you to learn things like a parrot. I want you to understand the underlying reactivity principles guiding these reactions as we see here. Right? So this is understandable in terms of nucleophiles and electrophiles. Right? Also understandable in terms of the Pearson-Hassab principle, where hard goes with hard, soft goes with soft, stuff like that. Now here, for example, so there we've used a Grignard reagent. You can also use an alkyl aluminium reagent, same thing. There's an example with chromium. There's the lithium reagent. You can also use zinc dimethyl or diethyl as an alkyl transfer reagent. So you have at your disposal all of these reagents, and basically the reactivity is the same. So that's a very common way of doing these, making these compounds. Another way is if we switch things around. So instead of having the nucleophile on the carbon, we now have the nucleophile on the metal. So a meta-centered nucleophile that we react with an alkyl halide. You see what we've done? We've swapped things around. So here's an example with sodium CP ion dicarbonyl. This is a hot nucleophile. So what were we doing here? What we're doing here is we take this one. So this is an anion. Sodium CP ion dicarbonyl represented there FP. Sodium FP. This is FP stands for this thing here. It's an anion. Now what's going to happen? What's going to happen? Think about it in terms of principles, nucleophiles and electrophiles. If I react this, for example, with methyl iodide, what's going to happen?
Well, the slightly positive methyl is going to react with the FP.
Yes.
And the sodium with the iodine.
Correct. So it's a nucleophilic attack on an electrophile. This is an electrophile essentially because this is pulling electrons away from the carbon. So the same principles in organic chemistry, really. And what's the product? The product is going to be sodium iodide. So it is also a metaparticle exchange reaction. And we're going to get the chloride, the methyl group here. So and there are many other examples of this. So here you see this is different from the first methodology we discussed, where we had it the other way around, where the nucleophile was on the carbon or the alkyl, and the electrophile was metal-centered. You see what we've done? We've swapped it around. Now the organometallic components is residing on the metal, and the electrophile is at the carbon. So that's another way of doing it, right? And there are numerous examples of this in the literature. Maybe I'll just give you another one. If you take sodium cyclopentadienyl, which is an anion, so sodium Cp, we'll discuss this in next week's lecture, and you react it with tungsten hexacarbonyl, this is a very cool reaction, you actually get this. Sodium, tungsten, this is tungsten 0, CO, CO, CO. Yeah, and that's a hot nucleophile, right? This reaction incidentally works, of course you eliminate 3 COs here. This reaction works only in very limited cases where you start off with a neutral carbonyl and you react it with an anionic C5H5. You get this hot species here, and then you can do the same chemistry as we did over there. For example, you can react this then with Rx, where X is a halide, and what are you going to get? You're going to install the R group on the tungsten. Well, that's another example. Point is we have a metal-centered nucleophile here. All right. Now this we've seen before. Here's our famous Vasquez complex, and we discussed this last year. I just have this here for completion. Oxidative addition. In other words, this is another tool we have in our toolbox. We can start off with an electronically unsaturated 16-valence electron complex, for example this one, but there's many other examples of course. And if we react it with methyl iodide, we get oxidative addition. So notice we're going here from iridium 1 to iridium 3. Oxidative addition always increases the oxidation state of the metal by +2. So 1 to 3. The reverse, incidentally, of oxidative addition is called what? Reductive. Correct. So if I were to start with this one and go back, I would, in principle, go back here. So oxidative addition, reductive elimination, inverse processes. Just, also we discussed this last year, just by way of revision. Interesting is, if you do the reaction with methyl iodide, you get trans stereochemistry, because the reaction follows a SN2 type mechanism, an SN1 type mechanism that we see in organic chemistry, so you get trans. Whereas if we do the reaction with dihydrogen, we get cis stereochemistry, because in the latter case, the reaction is concerted. In other words, here it's essentially a two-step mechanism. You have attack of this complex, which is behaving as a nucleophile because it's electron-rich, on the electrophilic carbon atom in one step. You form a, let's say, trigonal bipyramidal intermediate, and then in a second step, the iodine attacks, the I- attacks, and you get trans stereochemistry. Here, it's a one-step concerted mechanism where the H2 goes and sits on the iridium, and then you get an activation. It's also an oxidative addition. That's also iridium 3. See, iridium 1, iridium 3. But the stereochemistry is different. Well, this is a very interesting complex to study these things. But in the context of what we're discussing today, oxidative addition is a very important tool that we can use to make alkyl complexes, relying on the fact that they're electron efficient. Okay. Next example is insertion of alkenes, olefins, into metal hydride bonds. So if we have a complex that bears a transition metal hydride, what actually happens, it's a beautiful reaction. The alkene coordinates to the metal in the first step, and it inserts into the metal hydrogen bond, and what you get is an alkyl. That's an alkene insertion reaction. And this reaction, insertion of an alkene into a metal hydride bond, is actually the reverse of beta hydride elimination, which is something we're going to discuss in detail in a moment. So the forward reaction is insertion, the reverse reaction is beta hydride elimination. Is everyone following?
Yep.
Everyone following? All right. So that's an insertion into a metal hydride bond. We have other types of insertions that we can also employ. Here we have an example of a zirconium dihydride. If we react that with an alkyne, so a CC triple bond, two equivalents, we get a double insertion, and what we end up with there is also sort of an alkene component. Well, it's a sigma bonded carbon with a double bond in the back bond, right? It's an insertion. So instead of inserting a CC double bond into a metal hydride, we can also insert a CC triple bond. Then, of course, per definition, we will have still a double bond in the backbone. This is a very versatile reaction here, carbene insertion. We take here a hydride and we react it with, in this case, diazomethane. So this is, that should be CH3, not CH. No, that's correct, CH2. And this then, basically, what this is, it's a source of carbene, right? So you can think of CH2N2, I'll just write it like that. If this loses nitrogen, entropically, what are we going to be left with?
CH2.
Right, CH2. And then what is CH2? CH2 is a carbene fragment. So that thing is a hot reagent, very reactive. It attaches itself to the tungsten, and then it inserts in a second step into the tungsten hydride. So that's the way to think about it. So you have tungsten, let's just say tungsten H. This is generated by N2 loss. You get that. And then you can think of this carbene inserting into the tungsten hydrogen bond. And you get Ln tungsten CH3. Another tool that we have at our disposal. Everyone following. If you don't, stop me. We're going very fast. So if you don't understand something, stop me. Now we have another tool which is essentially the inverse of something that we call migratory insertion. So what we're doing here is we're starting off with a, we're starting off in this case with something like this. Here's an example from the literature. So there's a manganese carbon pentacarbonyl compound that's bound to this thing here, which is an acyl. We call this in CO, bound to a metal, is called an acyl functionality. And if we heat this up, we lose carbonyl. And what do we get? We get carbonyl flies away, and the carbon atom here binds directly to the manganese. You see what's happened there? It's we call this a reverse migratory insertion. The reaction can also go the other way, where we take this molecule here and we put it under a pressure of CO. The CO will insert itself into the manganese carbon bond. That's called migratory insertion. Now, this example here is not with an alkyl, but an aryl compound. So we end up with a sigma bonded aryl, but the same thing works for alkyl compounds. All right. So that's an example of an elimination, a CO elimination. Some people also call it carbonyl decarbonylation. This is an example that specifically, so this is now the 7th tool that we have. And this is actually what we were discussing this morning in the tutorial, weren't we? So this is work that was done by Bergman, 1982. And what they were trying to do was to activate alkanes. Now, why is that difficult? It's difficult to activate alkanes because carbon-hydrogen bonds are extremely stable. And what these guys did is they made this iridium complex that you see over there. This only works with iridium. So this is a special case for iridium. And if you photolyze this, you extrude hydrogen. So like I said to you this morning, the hydrogen flies away entropically, and you're left with a hot reactive iridium-1 compound. And then it can actually activate. It's so desperate for electrons, that intermediate iridium-1, that you get a CH activation reaction and you get something like that. So this is an example of a CH bond activation reaction. Here's just another example where you can photolyze it with neopentane, and you get essentially the same thing. So the principle is you start with a dihydride, which you access from the dichloride. This, incidentally, is a very versatile step reaction in organometallic chemistry, where you can convert metal halides to metal hydrides. You use something called superhydride. It's a reagent, LiBH3. Its action is that it basically converts, in this case, chlorine to H. And if you take that molecule, which is stable, and expose it to UV light in the presence of alkanes, it does CH activation. That's beautiful. Look at that. They managed to activate an alkane. That's amazing. Why is that amazing? Any reason why we think that is amazing? Alkanes are rocks. I mean, think about all this discussion about methane activation and stuff like that. So this is a very important scientific result, because it shows, at least in principle, that you can activate alkane CH bonds. What's the disadvantage of this?
It's only for iridium.
And iridium is what?
Freaking expensive.
Exactly. Exactly. I think you can do it in the meantime with rhodium. But yeah. All right, so that's sort of the toolbox, right? That's the toolbox. 7 ideas of how we can construct metal alkyl bonds. And I want to make something very clear. Don't just learn the reactions, understand what's happening. Right? Okay, now we get to something very important. The notion of an agostic interaction. Now, this term was coined in 1983 by Malcolm Green and Maurice Brookhart, 2 scientists, American scientists. Actually, I think Green was maybe British. Yeah, he was British, he was American. And what this is all about is the interaction between a transition metal and a hydrogen in the context of an alkyl or an aryl compound. And the way to think about an agostic interaction is that you have a metal, a transition metal, you have let's say some group here, some alkyl chain, and this is an agostic interaction. This is what we would call an alpha agostic interaction. So here you have a carbon-hydrogen bond that's interacting with a metal. It is a 3-centered 2-electron bonding interaction, similar to what we see, for example, in electron-deficient boranes, which I think you guys did with in the 2000 course at the beginning. Anyway, it's a 3-centered 2-electron bonding interaction where this metal with appropriate d orbitals forms a covalent interaction with this hydride. You see that? That is an agostic interaction. Now, we have different types of agostic interactions. We have alpha agostic interactions. This is an alpha agostic interaction because it's sitting on the alpha carbon. But if we have something like this, this would be a beta agostic interaction because it's on the beta position of the alkyl chain.
Is that still 3-centered though?
Yes, because we've got 3 centers. 1, 2, 3. Now that's an agostic interaction, and you can have gamma agostic interactions and so on. It all depends. You also have agostic interactions, incidentally, not with alkyls but with aryl groups. These also exist. So that's an example of an agostic interaction between a sigma bonded aryl H, an ortho H and a metal. These interactions are very important because they often are the precursor to the reactivity patterns that one often sees for transition metal alkyl compounds, for example, elimination and so on, which we'll discuss in a minute. Now, this whole story started in the 80s, but they published a paper, in fact, in 1983, these two guys, if you're interested. It's in the Journal of Organometallic Chemistry, a review article, where they first coined this phrase, or this term, agostic interaction, which comes from Greek, to hold close, right? That's what the metal's doing, it's holding the hydrogen. And the first example of this in the literature where this is discussed is this titanium complex. And what they did is they synthesized this and they performed a single crystal X-ray diffraction analysis where you can get very accurate bond lengths. And they noticed that the titanium-hydrogen bonding interaction, or the bond length, was 2.29 angstrom. Now, if one looks at the covalent radii of titanium and hydrogen, you will notice that that's a bonding interaction between titanium and hydrogen, covalent bonding interaction, should be around 1.6 angstrom. So this is obviously much longer, but they speculated at the time that there is some sort of an interaction between the titanium and the hydrogen. Now, the problem with single crystal X-ray diffraction analysis is when you're working with hydrides in the context of metals, it's not very accurate. Why is that? Again? When you're working with single crystal X-ray diffraction, it's not particularly accurate to look at a hydrogen atom that's sitting next to a metal. Why?
Because of the size. I mean, because of the electron density. And
Exactly. Good. The electron density of a metal, it's like David and Goliath. You have this huge metal with all these electrons, and you've got this tiny little hydrogen. And it's not accurate. So this is speculative. When you're working with transition metal hydrides, you have to do something called neutron diffraction, and that's been done subsequently. So this is the first example, 1980, of a neutron. So this is now this structure is, these bond lengths have been identified by neutron diffraction, which is much more accurate. And here again, so these bonding parameters here, 1.164 angstrom, is the distance between this carbon here and, in other words, this carbon here and the ion. And here you can see the distance between this hydrogen, which is forming an agostic interaction with the ion, is 1.87 angstrom. Now that's quite accurate. If you look at the sum of the covalent radii of iron and hydrogen, you will see that that is quite close to the expectations for an iron-hydrogen bond. Not exactly, but I mean, certainly, this can be classified as an agostic interaction. It means that the metal is pulling on that hydrogen, right? So you have this hydrogen and the metal is pulling on it. Do you see that? It's amazing. Okay, now that's an agostic, that's the story of agostic interactions, and they're very, very important in organometallic chemistry. Very, very important. Please understand the notion of an agostic interaction because you will see it everywhere. There are various consequences. First of all, sometimes they have a stabilizing effect. Here we have an example of a cobalt compound. Now, you can see it undergoes various sort of equilibria. Here we've got a di-alkene hydride. And basically what happens is this if we go from here to here, is that this coordinated alkene is inserting, remember our toolbox, into this cobalt hydride, forming this alkyl, and we have an agostic interaction. And that stabilizes the whole thing, right? So, and if we don't have this agostic interaction, the energy goes up. So this has been calculated. So agostic interactions are quite important. You also have the idea of an anagostic interaction. It's basically, the same thing as an agostic interaction, except the nature of the interaction between the metal and the hydride is that it is electrostatic. So in a formal agostic interaction, 3 center 2 electron, you have a more of a covalent type interaction, and in an anagostic interaction, it's electrostatic. The consequences for the lengths, right? So I mean, we have a certain range for that we can classify an agostic interaction, the distance between the metal and the hydride. Anagostic interactions tend to be much weaker because they're electrostatic. Yes?
I don't quite understand the difference between the two. Could you?
Yes, sure. First of all, the difference is in terms of the length. An anagostic interaction is a somewhat weaker interaction. And it's electrostatic, like the interaction between sodium plus and chlorine minus. That's an electrostatic interaction. Whereas in an agostic interaction, it's covalent, like the interaction between hydrogen and hydrogen. That's a covalent interaction. So here, electrons are being shared between the hydrogen and the metal, and in an anagostic interaction, it's just charge separation, and they're held together by electrostatics.
Got it.
Anagostic, anagostic. All right, so agostic interactions are very important in understanding the reactivity of transition metal-alkyl complexes. Right, and the most important thing in life when you're working with alkyl complexes is understanding the notion of a beta hydride elimination. This is the most common degradation pathway of a alkyl compound. Transition metal alkyl compounds, if they have beta hydrides, tend to be susceptible to beta hydride elimination, which is the reverse of what? Insertion. Alkene insertion into a metal hydride. So let's just write that down because it's of paramount importance. There's an alkene coordinated to a hydride. Insertion is the process whereby the alkene inserts into the hydride and we get this. Beta hydride elimination is the inverse of that, where we start with a transition metal alkyl that has beta hydrides and we get back to the alkene hydride. Now, this, in fact, is a more stable situation than this, right? Generally speaking. And the reason for that is, of course, because of the kinetic instability, as I said in the beginning, of a metal-carbon bond. But here you see the process, and it starts off with what sort of an interaction? What's that dotted line there? Consulu? Agostic. A beta agostic interaction. So we start off with a beta agostic interaction here, right? And then the metal basically grabs that hydride. So it starts off as an agostic interaction, they're interacting, and then the metal grabs the hydride all for himself. And then you get a formal beta hydride elimination. How does that work? Here's how it works. So you can think about, here's a metal with some ligands, alkyl, right? Here's an alkyl chain. There's a beta hydride. You have an agostic interaction between the metal and the H, as we see there. The agostic interaction gets stronger and stronger until what happens? The metal just plucks off the hydrogen from this carbon, and you get this process here where you end up with an alkene hydride. That is beta H elimination. Very important. And this is sort of the mechanism again, because it's so important. We start off with a metal alkyl. Here's the beta position, that's the alpha position. We have an agostic interaction forming between this H, a beta agostic interaction, or if you like, it could also in fact be an anagostic interaction. Point is, there is an interaction between the metal and the hydrogen, the beta hydrogen. That interaction gets stronger and stronger, and we get this intermediate here. Check it out. What's happened between here and here? Can someone tell me?
Between the alkyl transition?
Between there and there, what's happened?
You're breaking the metal bond. I mean, it's
The metal carbon bond breaks.
We're in the process. We're in the process. It's a transition state where this agostic interaction is becoming more of a hydride. So this carbon-hydrogen bond is becoming weaker and weaker and weaker, and the metal-hydrogen bond is becoming stronger and stronger and stronger. And then what happens next is we completely pluck off, the metal plucks off this hydride from this carbon, so there's no hydrogen bond anymore, and electrons are going from the metal to this carbon carbon bond here, and we end up with a hydride alkene. Beautiful. Look at that. Isn't that amazing? And you end up with an alkene hydride, and these alkenes can be, under certain circumstances, liberated from the metal, right? So that you end up, in the end, with some sort of a metal hydride and a free alkene. This process that I'm highlighting here is of key importance in alkene polymerization. Okay, is everyone following? Now, I want to just regress a bit, or digress, and just briefly mention the notion of an olefin complex or an alkene complex, because they're implicated in the reactivity of transition metal alkyl complexes. We did, I think, briefly touch on this last semester. Alkene complexes are essentially where you have, essentially an alkene coordinated to a metal. It's what we call an E/2 coordination, because the two carbon atoms are forming a bonding interaction with a metal. This is in fact the first example of an isolated alkene complex, 1831, Zeiss salt. The cation here is platinum. So this whole thing is anionic. This is platinum 2. These pictures come from Wikipedia. So sometimes Wikipedia has some nice things, right? So, yeah. That's how it looks. And the bonding interaction we can rationalize by the Dewar-Chat-Duncanson model. Remember, we've encountered this before. Where did we encounter this?
Last semester.
Huh?
Schrock, Fischer.
Yes, Schrock and Fischer, and before that?
High definition.
With the
Addition of hydrogen to the
Yes, yes. Sigma hydrogen complexes, but also with carbonyls. Remember? Now, the Dewar-Chat-Duncanson model you can always employ if you have a situation where you have a sigma donor, pi acceptor, a synergic interaction between a ligand and a metal. Like this. I give you your hand and I take your hand. Carbonyls do that, sigma hydrogen complexes do that, and so do alkenes. So what's happening here? We have a sigma donation originating from this pi bonding orbital to a metal d orbital, and we have a back donation from or also called a retrodative bonding interaction between the metal d orbital and the pi star orbitals. The pi star orbitals, antibonding orbitals of the alkene. Now, what are the consequences of that for the carbon-carbon bond? Look at that. Look at that, and tell me what would happen. Julia, will the carbon-carbon bond get longer or shorter? Yes. Why?
It's like they're antibodies, so they move away from each other.
Yes. Yes. I'm doing two things. I'm taking the electron density that's making up the double bond and I'm giving it to the metal. So that's going to lower the CC bond strength, isn't it? And I'm doing a second thing. I'm populating the pi star orbital with a back donation. That's also going to lower the CC bond strength. So what you get is that the bond order goes down from the formal double bond to, let's say, 1.5 or whatever. It depends on the strength of the back donation. You'd actually see that structurally. So this is a neutron structure, neutron diffraction, which is sort of the big brother of electron diffraction, you know, because that's really very accurate, but it's difficult and expensive to do it. These guys, so check it out. So here's the carbon-carbon bond, 139 picometers, or 1.39 angstroms. The bond length in free ethylene, however, is 133. So you see there's been an elongation of the carbon-carbon bond because of this situation here. We're populating the anti-bonding orbitals. Does everyone follow? Sure? Konsulu? Okay. So that's how alkene, that's an important class of compounds. They're ubiquitous in organometallic chemistry, so-called alkene complexes. Another consequence, incidentally, is of course, if the CC bond order is going down, another consequence is that we go from a formal flat as a pancake sp2 hybridized carbon that we see in free ethylene to a movement towards sp3 hybridized carbon, obviously. And there's a pyramidalization of the carbon atom. So it goes from being flat as a pancake to being pyramidalized, which kind of makes sense, right? Because you're killing the CC double bond character here by this population in the antibonding orbital. And so what you're going to end up doing is moving towards a, let's say, more sp3 hybridized carbon in terms of its character. Important stuff. Coming back to beta H elimination, it's a process that occurs very often with transition metal alkyl complexes. There are some general trends. I guess the most important trend is that as you increase the electronegativity of the metals essentially going from left to right, the effect of that is that the propensity of the complexes to undergo beta hydride elimination increases. And the reason for that is, obviously, if you increase the electronegativity of the metal, the agostic interaction, which is essentially the first step, if you will, of a beta hydride elimination, will also be increased, right? So that's the general trend. So if you have, let's say, for example, there are, of course, exceptions to this. This is really not always the case. But if you, for example, want to look at the, let's say, this relative stability to beta H elimination, let's say, of a nickel alkyl versus let's say, chromium alkyl, because the nickel is more electronegative, slightly more, it should enhance the propensity for it to do a beta H elimination. We can, of course, block this, fortunately. And how could we block it? So if we want to have a stable alkyl compound that doesn't die on us by beta H elimination, what can we do? Consume. Think about it. What would you do if you're a scientist and you want to block it? Just have no beta H's.
That makes sense, yeah.
If you have no beta H's, you can't undergo beta H elimination because there's no beta H. Here's some examples. Here you have a benzyl group. There's no beta H. In the beta position, you have an aryl group, benzene. Here there's no beta H. Alpha, beta. We have, in fact, no H's there. Here we have a beta H. The problem with this thing is, if it undergoes beta H elimination, it will form a CC double bond that's very, very constrained. Think, you can maybe do that as a homework exercise. Think about forcing this thing to undergo beta H elimination. You're going to get something very constrained that's not stable. So it resists the temptation to do beta H elimination. Here we have CME3, no beta H's, no beta H's, no beta H's. There we go, problem solved. Okay. However, I would like to say not all alkyl complexes undergo beta H elimination. There's many examples of complexes that are stable to beta H elimination. So there's all sorts of other factors as well that play a role. But generally, alkyl complexes, if you want to make alkyl compounds, one always has to think about beta H elimination. And beta H elimination, beta hydride elimination, is a very important, it's such an important thing. It is used, it is the last step in the synthesis of polymers, right? One of the most important discoveries of the 20th century was polymerization of ethylene by group 4 metallocenes. We have a task on this later on. We'll get into the mechanistic details. But what you essentially have is a group 4 metal, for example, zirconium or titanium. Hafnium also works, where you have 2 CP rings. And what you basically have is a mechanism to make polyethylene, where you have alkyl insertion. It's basically called the Cauchy-Ullmann mechanism. Maybe we should just look at that. It's called the Cauchy-Ullmann mechanism. And it's absolutely beautiful. So you have something like this. Now remember what I said this morning. Molecules have, complexes have personality. So let's say we start off with something like this. So this is a cationic zirconium-4 compound. And that little block there, it just means that there's a vacant coordination site. It's coordinatively unsaturated. Now, if I react this with, if I take this complex, which is the activated form of this metallocene or polymerization catalyst, and I bubble ethylene through it, C2H4, lots of ethylene, what's going to happen? Right? What's the first thing that's going to happen? This thing is electron deficient and it has a free vacant coordination site. What's going to happen? Where's the ethylene going to go? Josh?
Side, isn't it?
Yes, yes.
Yeah.
And how? It's just going to go and sit there. Yeah. It's going to. So let's do the stepwise. There's a. So it's going to go and sit there. I'm just going to draw the CP rings as circles. So it's going to go and sit there. What's the next step? What's going to happen next? Molecules have personality. Kunsulu.
I didn't know the copy of this.
Sorry, I'm going quite fast now. We're going to have, well, this is sort of like a hydride insertion. It's just an alkyl insertion. So the alkene is going to insert into the zirconium CH3 bond. It's exactly the same as a hydride insertion. It's just an alkyl, an alkene alkyl insertion. So see what's happened. That has actually, inserted. And now we have a vacant coordination. Well, actually, sorry, the vacant coordination swaps around just to get this right. So in other words, this forms a sigma bond to the zirconium, and the CH3 migrates up, and it forms a propyl, a zirconium propyl, with a vacant coordination site at the bottom.
So it just keeps going and going.
Exactly.
Polymerization.
Look at that.
That's clever.
So now the ethylene coordinates again, and what happens? We have another insertion, goes back down again. You see the chain is growing. 1, 2, 3, 4, 5. Now we've got a zirconium pentyl. What do we have? Vacant coordination sites. What happens? Keeps going, keeps going, keeps going. It's like a, look at that, look at that. It's like an enzyme. It's like something living. Imagine that. So you go up, down, insertion, coordination, insertion, coordination, insertion, coordination, insertion. This process happens so unbelievably fast. If you do these reactions, you see the polymers forming. So this happens like incredible amounts of times, and you end up, where it's happened a lot of times, with a very long chain, alkyl chain, and a free vacant coordination site. And then at some point, which is dictated by kinetics, what's going to happen? It's going to say, I've had enough. I don't want to do this anymore. And what's it going to do? Undergo what?
Beta hydrogen.
What?
It's going to eliminate itself?
Yes. By how? How? By?
Beta?
Beta hydrogen.
Beta hydride elimination. And what are we going to be left with? We're going to be left with, remember this is plus, we're going to be left with zirconium, a long chain, alkene, H. Right, so here's going to be this extremely long chain, beta H elimination. And then what's going to happen? The whole process is going to start again because the ethylene is bubbling through the solution. So what's going to happen is this is going to just be displaced by the ethylene. And we're going to get Cp2 zirconium, H, ethylene, plus is the polymer. That's called the Cauchy-Ullmann mechanism of ethylene polymerization. Now, I'm not going to go into details. This is something for a catalysis course, which in fact I will be teaching in the fall, where we're going to look at this again in enormous detail. But I will just say this. Depending on how you design the ligand sphere around the metal, you can change the chain length, because you can tune the rate of the insertion versus the rate of the beta hydride elimination. You can make long chain polymers, short chain polymers. You can do stuff like stereoselective reactions. It's just amazing. The point is, the last step in this very important process is beta hydride elimination. And all the plastic that you people use probably comes from this reaction, right? Yes?
I don't know if I'm getting too far into this, but once the beta hydride elimination has occurred, how can that zircon complex then be regenerated?
Oh, well, yes, it does. Yes, it is. So that's exactly what happens. You end up with this thing here, right, after all of these, after this whole beautiful process, and you end up with a beta H elimination, affording the zirconium hydride alkene. Because there's ethylene bubbling through the solution, all that happens is the ethylene, C2H4, displaces the polymer, so you now have ethylene, you now have a CP2 zirconium ethylene H+, and then the whole process starts again.
Oh, just straight away?
Yes.
Wow, okay.
So then the ethylene coordinates. There you have a hydride insertion, right? An alkene hydride insertion, and then we're back there again, except then we don't have a CH3, we have an H there, but it just goes on. It goes on. Amazing.
That's really cool.
Now, we've discussed beta hydride eliminations. This is the last thing for this lecture. Well, not really, actually, there's one other thing I want to discuss. We've discussed beta hydride eliminations where we start off with an alkyl compound. It undergoes beta H elimination, and we get an alkene hydride. Now, this is a variation on that, a variation on the theme, where we don't start off with an alkyl, we start off with a dialkyl. Okay, in this case, it's a chromium dialkyl. It happens to be a metallocycle. Actually, this is from my own work. This is from work I still did when I was at the University of Cape Town. And we studied this by computational methods. This is in the context of catalysis. But here we have a chromium dialkyl, and it does all sorts of interesting things. We end up here with this is called a metallocyclopentane. So this is a 7-membered ring system. And it undergoes, of course, as we just saw there, it can also undergo beta H elimination. But what's going to now happen is, instead of ending up with an alkene hydride, what actually happens is this. Because it's a dialkyl, the hydride in the beta position, as you can see, this has been characterized by density functional theory calculations. Here's the beta hydride. Look what happens to this hydride. Check it out. There he's sitting. This is the transition state. We have, what do we call that? Agostic interaction, a beta agostic interaction. And check what happens. The metal swings it over to the other side of the ring. It forms a sigma bond to that carbon atom. The metal-carbon bond breaks, so we have a CH3 that's free. And we have an alkene complex. So, in other words, it's exactly the same as a beta H elimination, but that under normal circumstances, if we just have one alkyl, right, we end up with Ln, sorry. That's the process of beta H elimination. Now, think about it. If you now have something like that, 2 alkyl groups, and one of these undergoes beta H elimination, what's the first step going to be? You can think of the first step as being having an H, having an alkene, and having that. You see that? That's what beta H elimination is. So if I beta H eliminate this ethyl group here, that's the consequence. Do you agree with me? Does everyone agree with me? An alkene H, and I haven't touched this, done anything to this alkyl.
Yeah.
Now, effectively, what happens here, we call this a beta hydride transfer is that you can think of what happens now in a second step, if you will, this is another way of looking at it, is that this then reductively eliminates. And you form LNM plus CH3CH3. In other words, what I've done there. So in other words, you have a beta-agostic interaction which facilitates the beta hydride swinging from here to here. The beta hydride goes boom across. And if you have a ring system like I have here, you end up with that. So that's what we call a beta hydride transfer. And I even wrote in my paper the agostic assisted hydride shift. So the agostic interaction, it's like a ship that ferries the hydride across. Right? Look at that. That's a transition state. And the beauty is, you can actually transition state in the software we had, you can animate, so you can see what it's doing. And if you animate this transition state, you actually see the hydride swinging across the ring as it's moving across from the beta carbon to the alpha carbon on the other side. It's assisted by a agostic interaction, yes.
Could you show the agostic interaction on your little general one?
Yes.
Just so I understand.
Well, what I've done here is I've sort of done it in 2 steps.
Yeah.
Which is not really what happens. It's a good question. What I've done here is I've said if we assume it follows a normal beta hydride elimination, this is what you would see. And another way of thinking about it is that it reductively eliminates, but generally the process is concerted.
Right.
In other words, you don't actually form this intermediate per se.
Mm-hmm.
I mean, that intermediate sort of resembles what I have there in the transition state. You see there's a hydride. This is starting to become an alkene. So kind of it's resembling that. But the way to actually think about it is really just let's draw it like this.
Uh-huh.
So that's the starting point, dialkyl.
Uh-huh. Agostic interaction.
We start getting an agostic interaction. The agostic interaction starts weakening this bond.
Yep.
What else happens? We start giving some electron density from the metal to this bond.
Mm-hmm.
And then this thing swings to the other side, and we end up with LNM. So it's actually, CH3, CH3. So you see, then that H, because this is a CH2, swings across there, and then this bond breaks.
Oh, I see, yeah.
And you eliminate, in this case, you would eliminate ethylene. You see that?
Yep.
In the example that I show you here, because the rings are attached, obviously it just it forms like a pendant thing. Cool. Now, I think that's fine. I don't think we have time to discuss these other eliminations. Maybe I'll just mention something briefly about that. Of course, we've discussed now at length beta hydride elimination, which is very important. We have other eliminations as well, alpha eliminations, gamma eliminations, etc. And we've actually already encountered one of them. Maybe I'll just discuss alpha eliminations. If we have tantalum neopentyl 3,
I remember this one.
This is the alpha position. This is how we make Schrock carbenes, remember?
Yeah.
What do we have? We have a so-called alpha hydride elimination, which works in exactly the same way. We have an alpha agostic interaction. That basically weakens the carbon-hydrogen bond. And as we just saw with that whole thing, the agostic interaction sort of helps the hydride across and gives this hydrogen atom to that group over there. And what do we end up with? What do we end up with, guys?
It's got 4 of those.
Carbene plus neopentate.
So that's an alpha hydride.
That's an alpha hydride elimination.
Yeah.
You also have gamma hydride eliminations, epsilon hydride eliminations. To generalize, generalize. Imagine we have a situation where we have an alkyl chain like this, alpha, beta, gamma, delta. They can all undergo eliminations. If we have an alpha elimination, what's the product going to be for this ring system?
See.
Alpha elimination, that will give, that will give
the H
CH3, CH2, CH2, CH4.
H and then the
alkene.
You just get a butyroalkene, right?
No, you get a copy.
Yeah, I mean, that's
Do you see that? Look what's happened here. It's exactly the same thing as here. Here we have an alpha H elimination, except in this case that H, there happens to be another alkyl group on the tantalum, so that picks it up, right? Like we just had with the beta hydride transfer. Here we don't have that. There's nothing else to pick up this H, so it goes and sits on the metal. But the result of an alpha elimination is always a carbene. What would the beta hydride elimination afford?
Beta elimination, so from, is that LNN, one methyl group,
Yes.
and the carb.
No, remember, beta hydride elimination always affords an alkene hydride, unless there is another alkyl group sitting on the metal which can pick it up, like we saw with that example with the ring. Difficult stuff, guys.
There's another carbon.
Alpha, beta, gamma, delta. And so on. Okay, incidentally, if we have a gamma, just for the sake of completeness, if we have a gamma elimination, we're going to get something like this. So that would be a gamma elimination.
No hydrogen.
Sorry, with a H. You see that? Beautiful. There's an example in the literature, just for interest, and then we're going to take a break. This complex, and maybe you can try this as a homework exercise. This complex, it's a platinum complex, can it undergo beta hydride elimination?
There is no.
Yes, there aren't any. So it's stable to beta hydride. You see, you can trick molecules. You can trick them. So these guys obviously wanted to make a platinum dialkyl, thinking it would be stable if they block the beta position. Unfortunately for them, you get gamma eliminations, delta eliminations, and epsilon eliminations. Alpha, beta, gamma. Oh, sorry, it's the wrong molecule, sorry. Let me just redraw this, sorry. By the way, that one can also undergo eliminations. Just ignore this. L2 platinum. This is the compound. That's the compound. So again, can it undergo beta hydride elimination? No. So these guys thought they were clever. They were going to make a compound that's stable. But you know what happens? It undergoes delta, gamma, and epsilon eliminations.
Okay, do
What
alpha.
about alpha?
Alpha, yes, it can undergo alpha as well. Alpha, beta, gamma, delta,
Epsilon.
epsilon. So there's actually two gamma positions. Three. These two and these two. And they each get different products. So you get a whole mess. So imagine the poor PhD student that was making that, saying, I'm going to be clever, I'm going to block the beta H elimination, and then did the reaction and it ended up with an NMR spectrum that looked like an exploded pharmacy because of all the products. That's what we used to say in Germany. You know, if you did a reaction and the NMR spectrum looked terrible, we say it looks like an exploded pharmacy.
I like that.
Explodierter Apotheker. So there it is. All right, so that's now, let's take a 5-minute break and reconvene for the next installment, which is Fisher carbines and short carbines.